In this lecture, we're going to continue our discussion on high-level language virtual machines. This lecture is the first part of a two-part sequence. So the execution model of modern programming languages and their implementations, languages like Java, the .NET languages, scripting languages like Python and Ruby and JavaScript, are typically object-oriented. Object orientation gives us the great features of encapsulation and data hiding, inheritance, and polymorphism. Polymorphism being where we use the same names to represent different techniques or functionalities or attributes in an object. We discussed last time some background material on object orientation. So you should be familiar with static methods and what static dispatch is. Static methods are dispatched statically based on the type of the variable. Virtual methods use dynamic dispatch. C++ and C# have dynamic dispatch for methods, instance methods marked as virtual. And languages like Java and Python don't use the virtual keyword, but have every single instance method in objects dynamically dispatched. Dynamic dispatch means that we look at the underlying type of the object at runtime, and we invoke the method defined by that type. For instance methods that are dynamically dispatched, they are overridden by the child if the same name is used in the inheritance hierarchy. For everything else, for fields, for static methods, fields, instance fields or static fields, they're all hidden, not overridden. That means that if you inherit an instance field or a static method from a parent, and you create a child with a field or method of the same name, both are available at runtime, and you can get to them through casting. Another feature of modern programming languages is that they're portable and assumed to be mobile. That is, the representation of the program is architecture independent so that we can ship it around over a network and load it from different locations and execute it on any machine. This write once, run anywhere model is another way of establishing portability so that program developers do not have to port their code to each architecture or operating system on which they want to run. They simply use a runtime system that has been ported to those architectures and operating systems. And if their programs execute in that runtime system, then their programs are portable. The way this works is that we represent programs in compact but architecture independent representations of the program. This could be source, but typically it's binary. It's a compact representation of the source. The pieces of the program are typically incrementally loaded, so they can be loaded from different places. You only load and transfer what you're going to use during execution. It's really a principle of laziness. That is, you only do the work necessary for the particular execution of the program that is happening right now. You're not going to load the entire program if you're only going to use a piece of it. You're not going to translate class files that you're not going to execute or use in any way. When you have an architecture-independent representation of the code and data in these class files that are being transmitted around, once at the target destination, we have to translate that architecture-independent representation into code for the underlying physical architecture, that is the native code that underlies the runtime system. So the runtime system is in charge of doing this translation, and typically it translates a little bit and executes until it touches a new piece of the code that hasn't been loaded or that hasn't been compiled yet or translated, and translates that. So it's interleaving translation to native code with the execution. You can do this a couple ways, and we're going to get into this in detail in this class. You can do it line by line, that is instruction by instruction, and that's called interpretation. Or you can do it multiple instructions at a time at a method level, or maybe a path through a method. And these techniques are called compilation And you've probably heard of just-in-time compilation or trace compilation. We'll talk more about these when we get to it in this class. So the model of execution is that you write source in a high-level, verbose programming language that really facilitates readability by others, by humans. We then translate that source, which is in an architecture-independent format because it's source text, and we convert that to a more compact binary representation of the program. Now, this program still is architecture independent. It will not run on any physical hardware as is, but it's more compact, so we can ship it over the network. And at the target destination, we have a runtime system which translates this compact architecture independent representation to executable code. The runtime system is in charge of loading and verifying the program is correct and whole, hasn't been modified. In some cases, like for Java, it checks for type safety. It performs memory management. That is, when you create an object and you stop using it, you no longer can reach it, let's say. The garbage collector will clean that memory for you. Other things that the runtime system is involved in are threading, multi-threading, and synchronization of using locks, and also optimization. While the program is running, we can improve how it's laid out, what instructions are executed to make it run faster, or perhaps extend the battery life of the underlying physical machine. In Java, these class files are what we're going to study next. The class files are broken up into two pieces. There's the symbolic information, which is the names of all of the attributes and properties and fields and methods that you're going to use in the class. And then there's the code itself, the methods that are going to be executed by either the class or objects, instances of the class. Each class file is in a binary bytecode format, a compact representation of your source. And the layout of this class file is fixed and well-defined. Every single byte has a place and is in a particular order. That makes it really easy to check for, structure problems, and it makes it really easy to find things, because what we're going to have to do once we transfer this over the network is load it into memory and create an internal representation of the class so that the runtime can make use of it in its translation. The symbolic information, if we're talking about the .NET language, it's called metadata, but it's very similar to what's in Java class files. This is all of the data, all of the symbolic names necessary to execute the class file. Both have to be transmitted together so that we can execute the class and create objects from this class. And in the methods themselves, there are series of instructions of the functionality that you've coded in your source programs. This code is a series of instructions that come from a well-defined instruction set architecture. Now, this is an architecture-independent representation. It's an instruction set architecture that doesn't necessarily map to any physical machine. This class is as compact as possible. Instead of repeating, let's say you use, int I in all your methods, you're not going to have, a copy of int I for each method. What you're going to do is you're going to have the name int and the name I represented in the constant pool in the data, metadata, symbolic information area of the class file once. And then every time you access I in your methods, you have an index into that constant pool to indicate what the name of that variable is. Constant pool is a well-defined structure that has a table and a set of indexes, and what's in this table are all of the types that you use, the packages, the classes, any primitives that you use, any constant values that you use, all names, also your method and fields are all represented in this symbolic information of a class file. Here's an example of what the layout looks like. Excuse me. The layout, again, is well defined. Starts off with the magic number, which is a unique identifier just to indicate that this is a Java class file. Then the constant pool table is there. This is the table of symbolic information. And then we have other information about the class, like the access flags, whether it's publicly accessible, part of some package. You have the references into the constant pool for the name of the class, the name of the class's parent, its interfaces, all of its fields and methods, and any type of other attributes it may have. So in this example, the constant pool might look like this. At the very top, you might have entries in the table that are string, that actually have a string constant like hello. You'll have names of methods. Method M is in class C, and it takes an int as a parameter. It has one parameter. I'm sorry. Returns doesn't return any value in this case. You might have a field as a type int. Its name is F. All of that all those names are represented in the constant pool. The fields are data structures that describe the fields that this class implements. The methods are data structures for the methods that this class implements. Again, these are going to be static or instance methods. Either one are both given representations in these data structures. When these data structures reference a symbol, a name, they simply have an index into the constant pool. Methods have an attribute, which is an array, which holds the actual code. The code is just the list of instructions that the method implements, and there's other attributes associated with this. We'll talk about max stack later, but it has a piece of data that indicates how many local variables are being used, what exceptions are called, and there may be some other attributes like where the source is in the file. Again, all of the instructions in a method, when they access fields or methods or strings or constant values, just simply index into the constant pool to get those names and values. When a class file is read in from memory read into memory from over a network, the runtime takes the class file and makes its own internal representation. Different runtimes can do this a little bit differently. How it lays it out in memory is really up to the runtime, but the idea is you want to have a very easy way to get to a class structure, to figure out what fields are in a class, what methods are in a class, what objects might look like that are created as instances of this class. The runtime also keeps a big global table that refers to these different structures, again, just to make it really easy to access as I'm loading new classes, and those classes access classes that are already loaded. We need to be able to link those together, and so these tables facilitate that lookup process. All internal structures that the runtime needs to get to, and class representations, static fields, static methods, are all stored in a table called a global table, or sometimes called a statics table. So we just keep track of everything static, and then we have individual data structures for the internal classes. The bytecode instructions have to facilitate Turing completeness. They are a set of instructions that are very simple, very compact. They are variable in length. They do everything you need to do. You have to be able to load and store information from memory, data from memory. You need to perform arithmetic and logical operations. You need to be able to convert types, do casts. You have to be able to create objects and manipulate objects, read and write their fields, check properties. We need to be able to perform operations, and we're going to do that with what's called an operand stack, and I'll talk about that more. We need to be able to jump around in the code, maybe with conditionals like if then else or go-tos. We need to be able to invoke methods and return from them. We need to handle exceptions, and we need to perform a synchronization. All of this is built into the bytecode instruction set architecture for any language, but we're going to focus on the Java language here. So let's talk about this operand stack. This should not be confused with the user stack or the runtime stack or the system stack that you may have heard of in your operating systems class. This is different. This is a way that we're going to perform operations in the instructions. Remember, we said that we need to have a representation of your source program in a very compact representation. This compact representation is designed so that we perform all of the operations on data structure that's in memory. So if you want to perform an add, you're going to push the values you want to add on the runtime stack to hold the operands that you want to perform the operation on. The operation then consumes the values from the operand stack, performs the operation, and pushes the result there. This is called a LIFO data structure, last in, first out queue, where you push your operands onto a stack to perform the necessary operations on them. In modern languages, the operand stack is typically used to execute a stream of instructions, and I'll show you what that looks like next. The virtual representation of the architecture, the virtual architecture that the instruction set represents, is called a stack machine. So in this example, we have a series of instructions that implement the source instruction C equals A plus B. What we're going to do is convert that to instruction set architecture, a series of instructions in the Java bytecode language. In order to do that, we want to do this in a very compact way. So we're going to have a virtual data structure, and that data structure is called the operand stack, and that's where we're going to put our operands to perform our operations. So the first thing we do is we push A onto the operand stack. TOS stands for top of stack. We then push B on the top of the stack. Add then has no operands. Add knows to go to the operand stack, take the top two values, consume them, that is, pop them off, perform the operation A plus B, and to push the return value onto the top of the stack, TOS. We then need to store whatever's on the top of the stack into C, the local variable C. A, B, and C are all local variables here. In order to do that, we need to pop that off the operand stack to put it into the local variable. What this does is provides us a very compact instruction encoding, because we don't have to encode any of our operands, or we have to encode very, very few. For example, we don't have to encode any operands with add. This stack-based architecture is very simple. It's very easy to write very simple runtime systems called interpreters from them. We can actually implement this stack-based virtual architecture using real hardware. There's a device called the Java card that does so. There's also a processor called the Azul Vega that does so, but they're less common. So the idea is we're going to ship the program in this architecture independent representation, and then we can optimize it, we can translate it to the native code on the fly, because it's really easy to manipulate and it's very compact. We have alternatives here. We didn't have to do it this way. We could have used other representations that are more similar to the machines we use today. The two most common representations of ISAs are register-based ISAs. These are instruction set architectures that assume that there's registers in the machine. Most machines today have registers, physical registers. These are physical locations in the processor that holds data, and operations are performed on those locations in the processor, and it's really fast since we don't have to go to memory. It's like caching information in the processor itself. So we hold the data there so we can perform the operations and the instructions really fast. There are two types of register-based ISAs. The first one's called a register-register ISA, or a load-store machine. This is where memory accesses are done via load and store instructions only, and all other operations are performed on registers. So you move the data from memory to registers, and then you perform the operations on registers. as shown in the example. This is another name for this type of architecture is RISC, Reduced Instruction Set Architecture. The alternative to register machines or load store machines is register memory. This is like the x86, which is a CISC machine, complex instruction set. In this case, the operands in an instruction, an ISA instruction, can be taken from memory or can be in registers, either one. This allows you to have many fewer instructions, but you really don't know how each is going to perform because you don't know if you have to go to memory to get those values or to cache, or if those values are going to be in registers. So the same instruction would operate on data from different places in the architecture. We could have represented our Java bytecode in a format like one of these, but it'd be less compact because we'd have to encode all of our operands in each of the instructions. With a stack-based machine, we have to encode much less because we assume we have this hidden data structure called the operand stack that we're going to have when the program actually runs in memory, and we can read and write our operands from it. You should be able to tell me what the trade-offs are between these different instruction set architecture representations. The instructions in Java bytecode are typed. We have an instruction that's made up of an opcode, which is 1 byte in width, and then there's a series of operands, one or more. The instruction itself is variable length, depending on how many operands there are. You can tell how long it's going to be by looking at the opcode. Each opcode represents an operation. That operation is typed. What that means is that if you have an add, the operand, the opcode is going to be an add on a particular type. So there's going to be an iadd for integers, an ladd for longs, an fadd for floats, a dadd for doubles, and so on. And this is nice because then we know exactly what hardware instruction we're going to be mapping this to. We don't have to try to figure out the types of the operands on the fly. We know that the operation has a certain type, and therefore the operands have that same type. When you have a method in Java bytecode, you have a couple of other data structures as well. You have this virtual operand stack that the instructions use to perform their operations. They move data from local variables. We have a local variable array, which is a data structure that holds all of the parameters, the arguments that are passed in, and then that's followed by all of the local variables. So if I tell you the length of a local variable array, you know how many parameters plus local variables it has. The operand stack is used to do all of the operations. We're going to move data from the local variables to the operand stack and back using bytecode instructions. There's also that constant pool, that internal representation of all of the symbolic information. Some of the instructions reference the constant pool, as I mentioned before. They reference the constant pool to get to names. Say you're going to invoke a method in an object of another class type. The instruction is going to have a method call invocation and an index into the constant pool. That index represents the name of the class, which is the type of the object, and the method that you're calling, so that we know how to invoke that method at runtime. This is an example of Java bytecode of a very simple program that I give you handout information from on the web page. It has a class called simple, and on the left is the Java source. On the right is the bytecode. You can look at the difference between the two and try to understand what instructions map to what bytecode instructions. On the right, we're going to load a local variable at index 0 onto the operand stack. We're going to figure out how long that object is. That object on the operand stack has to be an array. An array is held by a reference. So the first instruction, 0, a load, has an A in front of it. It's prefixed by A because an A is a reference type all instructions are typed. The second instruction, array length, takes the reference that's on the top of the stack and computes its length, and so on. All of the instructions have a meaning, and I give you a reference on the web page to this a web page that describes each of the operations that are listed here in bytecode. You should be able to tell me exactly what each instruction does, and we'll practice this together in class. When a method call is made, if we're using interpretation, which is line-by-line execution of bytecode, the runtime moves the arguments to the correct location in the caller's registers in its local variable array so that the target method can be invoked with the variables that are passed in, the arguments that are passed in. Just again to give you a feel of the Java virtual machine bytecode instruction set versus others, the JVM bytecode is typed instructions. Each opcode is 1 byte wide. That means there's 255 possible opcodes, 253 are used. The operands, there can be 0 of them, there can be none of them, like add, and they can have more. So the instructions are variable. In .NET, MSIL is the intermediate representation for .NET programs. They do the same thing. The instructions are typed, only in this case, the opcode is 2 bytes in length. So therefore, there's 64K possible operations in the bytecode language for .NET. Python has 113 opcodes. 42 have arguments, 71 do not. They're all variable length. All use an operand stack for one or more of their operands to perform computations in the virtual representation of the program. The translator must translate this virtual machine model to the native code line by line or multiple lines at once. And we'll talk about that translation process to get it out of the stack-based machine and onto a physical machine, which usually is a register-based machine. And that's called translation, interpretation, or compilation. And we'll talk about that in later classes.